This is problem 12 from chapter 17. The problem reads, consult multiple concept example 3 for background pertinent to this problem. A speaker has a diameter of 0.3 meters. Assuming that the speed of sound is 343 meters per second, find a diffraction angle theta for a 2 kilohertz tone. And B, what speaker diameter D should be used to generate a 6 kilohertz tone whose diffraction angle is as wide as that for the 2.2 kilohertz tone in part A. So, part A asks for us to find a diffraction angle for a 2 kilohertz tone. First thing we have to do is, actually solve for our wavelength using the equation lambda equals velocity over frequency. After we attain that value for our wavelength, we are to plug it into this equation here to solve for theta. Well, this equation here is if we are dealing with a rectangular area, and this one here is for dealing with a circular. But in the first case in this problem, and as it relates to the example in the book, the speaker in part A is actually circular, so we know to use the second equation here. But in part A, I solved for lambda first, like I said we needed to, and I found my lambda to be 0.1715 meters. And the D, which is given to us in the problem, we know is 0.3 meters. So with that, I did the inverse sign of lambda over D times 1.22, and I got an angle of 44.22 degrees. And for part B, it asks us what speaker diameter D should be used to generate a 6 kilohertz tone whose diffraction angle is as wide as that for the 2 kilohertz tone. All this is basically saying is that we're going to use the same diffraction angle from part A, but we're going to have a different wavelength just because we have a different frequency. So the velocity stays the same. We use our new frequency to determine our new wavelength, and we do pretty much manipulate this equation here to solve for our new our D value. So once we do that, we attain, once we get our new lambda value, we have our same theta value. We do the math and we get D to be 0.08 meters.